Hello there and welcome back to this video series on control systems. In the last video, we have seen what a servo motor is, and we have seen that DC motor action can be either through armature control or field control. We have seen a little bit about what is armature control and field control and brought out their comparative features. We'll continue from where we left and try to consider schematic of DC motor under armature control. This shows the armature schematic. These two are armature terminals. This you may think of as brushes, and this is the rotor on which armature windings are placed. The motor has a motor shaft. That shaft carries an inertia and a damping. The net inertia either on the motor side or on the load side, everything brought together onto the motor side is J equivalent. All the inertia brought onto the motor side is F equivalent. Then the resistance and inductance of the coils inside this armature, they are shown externally for clarity. The net resistance is Ra, the net inductance is La, and across the terminals a voltage of EA is supplied, E lowercase and subscript A. Along with this armature voltage, if you supply a constant field voltage, field is EF, field current is IF, I sub F, E sub F. When you supply this, magnetic field is established, and when that field cuts the armature conductors, you have a torque Tm generated. Because of this torque, the motor shaft turns. When the motor shaft turns, armature coils also turn. When they turn, a back EMF is manifest across the armature terminals. This EB is the back EMF which opposes the voltage applied EA because of Lenz's law, or you may say due to second law of thermodynamics as well perhaps. While all this is happening, an external disturbing torque TD may be acting on the motor. We will try to write the equations for this system and try to develop a block diagram. Okay, the nomenclature is listed over here. IA is armature current, EF, IF are field currents, EA, IA are armature currents, omega m is the angular velocity, theta m is the angular displacement, J equivalent, F equivalent are the inertia and damping, TD is the disturbance torque. While attempting to write equations and develop block diagram, we'll consider 4 segments of this system. One segment is this RA, LA, EA and EB. Okay, that is what we call armature circuit. Second is the motor action, that is current carrying conductor, magnetic field and torque generation. The third is the load section, how Tm moves this J equivalent and F equivalent, and fourth segment is back EMF. So there are 4 parts. One is the armature circuit, 2 is the motor action, 3 is the load section, and 4 is the back EMF. We'll carefully consider each section and write equations for them. Let us begin with the armature circuit. We see that the voltage applied EA, go back and refer to the diagram, EA should be sufficient to pump the current through the inductance and then pump it through the resistance and then overcome the back EMF. That we can say that we can see here. This EA should be sufficient to pump it through RA, pump the same current through LA, and then overcome this EB. It would be helpful if you draw this diagram on a piece of paper, keep it in front, and then watch the video. Okay. So we write one equation as EA is equal to LA di by dt. This is the voltage drop across the inductor. Then RAIA, this is the drop across the resistor, and this is the back EMF. We'll take Laplace transform of this equation, assuming initial conditions to be zeros. So lowercase EA has a transform uppercase EA in Laplace domain. Then EB has capital EB, RAIA, RA capital IA, and you have a derivative here. So one multiplication by Laplace operator S. And then we can further simplify this. Very many times when you have to write the same equation over and over with slight changes, we omit this S in the parenthesis. EA is equal to EB plus LASIA plus RAIA, leaving S in the parenthesis. When it is understood that it is in Laplace domain, why write it many times? So we rearrange it, EA minus EB written over here. EB, take it onto the other side, EA minus EB, and take IA outside, LAS plus RA. This is one equation we have, for which we can draw a block diagram as shown here. Plus EA minus EB divided by this is equal to IA. We know that the torque generated by the motor is proportional to the magnetic flux and armature current. So we can write torque generated by the motor in Laplace domain is K phi IA of S. Further, we know that the field generated is proportional to the field current IF. As you keep on increasing IF, the field also increases up to a saturation point. Beyond this point, the field doesn't increase. So we'll assume we are operating in this region with the slope Kf. And thus we can write in the linear range, this flux is equal to some constant of proportionality multiplied by the current IF. So you take this value of phi, substitute here. So we write Tm is equal to K, Kf, If into Ia. These three quantities put together, we call it Km. And so we have motor torque is Km multiplied by Ia. And this we write as a block diagram here. We take Ia, multiply by Km, you get Tm. Again, we look at the schematic diagram of the motor. We just go back a little bit and look at the schematic. This torque Tm generated by the motor should be sufficient to move this inertia, move this damper, and then overcome the disturbing torque. Noting that we can write one equation as shown over here. The torque required to accelerate the inertia is d square theta by dt square multiplied by J equivalent. Similarly, it is the first derivative here, and we take Laplace transform on either side to obtain an equation given in 3 here. You can carefully follow through them, write the equations one after the other. You can see it very clearly. And so this omega m comes out to be Tm minus Td. If you take this Td onto the other side, it becomes minus Td, and divided by J equivalent S plus B equivalent acting on omega m. With this, you can draw the block diagram shown over here. Plus Tm minus Td divided by this is equal to omega m. The next section that we are going to write, equation 4, is the back EMF. okay, which is again an electromagnetic phenomenon. Okay, the back EMF is proportional to the speed of the motor. With constant of proportionality, we call it back EMF constant. So with this, we can write one equation as EB is KB into omega m as the input, KB is the constant, EB is the output. You can note and derive that KB is equal to Km if the efficiency of conversion of electrical energy to mechanical energy is 100%. Okay, with this we write the equations one after the other to summarize. So this is the equation for armature circuit. This is the equation 2 is the equation for motor action. Equation 3 is for load section, and equation 4 is for back EMF. For back EMF, this is the block diagram we write. Now we carefully connect these things to form the overall block diagram. Okay, these are the 4 block diagrams we have. 1, 2, 3, 4 block diagrams. You can see that IA appears here and appears here. So we can join this line and this line. Let us do that. Okay. Then you can see that you have motor torque Tm appearing here and motor torque Tm appearing there. So you can join them. Join. Then you see omega m appearing here and omega m appearing there. You can join the two. This gives the overall block diagram of the armature controlled DC motor. Okay, you can see that there is an inherent feedback loop. All this is feed forward direction. This is feedback direction. There are 2 inputs, 2 arrows coming into the system boundary. One is EA, second is TD. We can, if you simplify this block diagram, how to simplify we'll see later, but if you simplify this block diagram, you have omega m output is something multiplied by EA minus something multiplied by TD. Okay, so this G1 and G2 may be derived as shown over here. I think we'll stop here and give the summary. We can summarize that we have considered a DC motor and equations for individual sections are written. Those sections are 1 armature circuit, 2 motor action, 3 load section, and 4 back EMF. And we have written the equations, drawn the block diagram, and presented 2 transfer functions. I think that's all we have, and have a great day.